Right now, light is crossing the distance between the Earth and the Moon in just over 1 second. Not traveling, not racing, simply existing at a speed so absolute that the universe itself appears to have been engineered around it. 300,000 kilometers every second. A number so precise, so universal, so stubbornly consistent across every experiment ever devised, that scientists began to suspect it wasn't describing light at all. It was describing something deeper, something structural, something that held the reality together at its very seams. For centuries, that number sat in our equations like a locked door. Impressive, unexplained. And when the greatest minds of the 20th century finally forced it open, what they found on the other side wasn't just physics. It was the hidden architecture of time itself. Richard Feynman didn't just explain why light travels at this speed. He revealed why nothing can exceed it. And the answer, once you truly understand it, would permanently alter how you experience every single moment of your life. In 1638, on a quiet hillside outside Florence, a man held a lantern against the dark and asked a question that would echo for 300 years. Galileo Galilei had recruited his assistant, positioned him on a distant hill across a pitch-black valley, and constructed the first known experiment designed to catch light in the act of moving. The plan was elegant in its simplicity. Galileo would uncover his lantern. The moment his assistant saw the flash, he would uncover his own. Galileo would measure the gap between sending the signal and receiving the reply. He measured nothing, or rather, he measured a gap so vanishingly small that he couldn't distinguish it from human reaction time. Light, if it had a speed, was moving faster than his instruments could resolve. He concluded with characteristic honesty that if light wasn't instantaneous, it was at minimum 10 times faster than anything he could detect. The question remained open, suspended, waiting. 38 years later, a Danish astronomer named Ole Rormar sat at the Paris Observatory, watching something that nobody else had thought to watch carefully. He was observing Io, one of Jupiter's moons, tracking the precise moments it disappeared into Jupiter's shadow and re-emerged on the other side. He had a problem. The eclipse times didn't match his predictions. When Earth was closest to Jupiter in its orbit, Io appeared early. When Earth was on the far side of the Sun, Io ran late, by nearly 22 minutes. Every other astronomer assumed the discrepancy was an error. Who not understood it was a message? Light wasn't arriving instantly from Jupiter. It was traveling to reach him. When Earth moved farther away, the light had more distance to cross. When Earth moved closer, less. He calculated the speed, approximately 220,000 kilometers per second, remarkably close to the truth given his instruments. For the first time in history, light had a measured velocity, but nobody fully understood what that number meant. 2 centuries passed. James Clerk Maxwell sat with a set of equations describing electricity and magnetism, and noticed something extraordinary buried inside the mathematics. His equations predicted the existence of electromagnetic waves, and when he calculated the speed at which those waves would propagate through space, the answer stopped him cold. It was the same number, the speed of light. Maxwell realized he hadn't just described electricity and magnetism, he had accidentally described light itself. Light was an electromagnetic wave, and its speed wasn't a property of the source or the medium. It fell directly out of the fundamental constants of electromagnetism. It was, in some profound sense, inevitable. But if light was a wave, it needed something to travel through. Water waves need water. Sound waves need air. Physicists invented the ether, an invisible medium, filling all of space through which light vibrated. They were certain it existed. They just needed to find it. In 1887, Albert Michelson and Edward Morley built an instrument of extraordinary precision, an interferometer capable of detecting the faintest variation in light speed depending on the direction of travel relative to Earth's motion through the ether. If the ether existed, Earth would be moving through it like a ship through water. Light traveling with the current should move slightly faster than light traveling against it. The difference would be measurable. They measured nothing. Absolutely nothing. No variation. No current, no ether. The experiment failed to find what it was looking for, and in doing so, it shattered most fundamental assumption in physics. Light moved at the same speed in every direction regardless of how fast Earth was moving, regardless of how fast the source was moving, regardless of anything. That results that in the scientific community like a splinter, impossible to ignore, impossible to explain for nearly 2 decades. Then came Albert Einstein. In 1905, at 26 years old, working as a patent clerk in Bern, he did something no physicist before him had dared to do. He stopped trying to explain why the initial summary result was wrong. He accepted it as truth. He built his entire theory around it. If the speed of light was the same for every observer in every reference frame, then the things we assumed were fixed, time, distance, simultaneity, had to be flexible. Space could compress. Time could dilate. Two events that appeared simultaneous to one observer would not appear simultaneous to another, moving at a different velocity. The speed of light wasn't just a property of electromagnetic radiation. It was a structural constant of space-time itself, a cosmic conversion factor between space and time. The number that appeared in the most famous equation ever written, E equals mc squared, as the bridge between matter and energy. But Einstein's relativity told us that nothing could exceed light speed. It didn't fully explain why. The mathematics showed that accelerating any object with mass toward the speed of light required infinite energy. The equations broke down. The answer became undefined. But the underlying mechanism, the deep physical reason, reality refused to cooperate, remained elusive. That deeper answer would wait for Feynman. Richard Feynman approached quantum physics the way a sculptor approaches marble, not trying to impose a shape, but listening for the form hidden inside the stone. In the 1940s, he developed a framework called the path integral formulation of quantum mechanics, and embedded within it was something that would finally illuminate the mystery of light speed at the most fundamental level imaginable. Here is what Feynman uncovered. A particle moving from point A to point B doesn't take a single path. Quantum mechanically, it takes all paths simultaneously, every possible route, every wild detour, every impossible shortcut through space. Each path contributes a probability amplitude. Paths that are wildly different from the classical trajectory tend to cancel each other out. Paths near the classical route reinforce each other. The particle behaves as though it traveled the most probable path because all other paths destructively interfere. Now apply this to photons, light particles. In a quantum field, a photon propagates through our possible trajectories. Every path that would require exceeding the speed of light, every path that would violate causality, those paths destructively interfere with devastating efficiency. They cancel. They annihilate each other in the mathematics. What survives, what constructively reinforces, are precisely the paths that travel at or below light speed. The speed limit isn't imposed from outside the universe like traffic regulation. It emerges from the internal logic of quantum fields. It is the natural consequence of how probability amplitudes interfere when particles move through space-time. To exceed the speed of light would require a configuration of quantum paths that simply cannot constructively interfere. The mathematics won't allow it, not because of an arbitrary rule, but because of the deepest structure of reality itself. But why does this matter? Why should the cosmic speed limit concern someone sitting in a room on an ordinary afternoon? Because it defines the boundary of your reality. Right now, your observable universe extends approximately 46 billion light-years in every direction. Beyond that horizon lies space that exists, that contains galaxies, that has its own structure and history, but that you can never see, never reach, never know, not because of technological limitations, because the light from those regions has never reached you and never will. The expansion of space is carrying them away faster than light can cross the growing distance. You live inside a bubble of causality. Everything inside it can, in principle, affect you. Everything outside it cannot. The speed of light is the membrane of your existence. When you look at a star 40 light years away, you're not seeing it as it is. You're seeing it as it was 40 years ago. The star you're observing might not even exist anymore. The night sky is not a window. It is a museum of the past, a record of light that left its source decades, centuries, millennia before you were born. And here lies the most profound implication. The speed of light isn't just the fastest thing in the universe. It is the maximum rate at which information, cause, consequence, and reality itself can propagate from one place to another. Break it, in effect, could precede cause. A message could arrive before it was sent. Time's arrow would shatter. Logic would unravel at the quantum level. The universe, as a coherent, self-consistent structure of cause and effect, would cease to function. Galileo had a lantern against the darkness and caught nothing, because light was already moving faster than he could imagine. Norman watched the moon disappear into shadow and heard the universe confessing its own troubled time. Maxwell found the speed hiding inside the mathematics of electricity and recognized it as the speed of light. Michelson and Morley built a machine to catch the ether and found empty space staring back at them. Einstein accepted the impossible result and rewrote the architecture of reality. Feynman looked deeper still and found the speed limit, written into the interference patterns of quantum probability itself. Each generation inherited a question and returned an answer that generated a deeper question. That chain is not finished. It may never be finished. But what we know now, with extraordinary confidence, is this. The speed of light is not a rule imposed on the universe. It is the rhythm of the universe, the tempo at which reality updates itself, the rate at which cause becomes effect, the clock frequency of existence. To exceed it would not merely break a law of physics, it would break the logic that makes physics possible. You are alive inside a cosmos that communicates with itself at exactly 299,792,458 meters per second. Not faster, not slower. Precisely that. And the fact that this number exists, that it is finite, that it is the same everywhere in space-time, tells you something extraordinary about the nature of reality itself. It is ordered. It is consistent. And somewhere inside that consistency, there may still be mysteries that no lantern has yet illuminated. If this video shifted something in how you see the universe, hit that like button and subscribe. There are more questions where this one came from.